Okay, I'm Jim Frankfield, and this video is going to be on prime numbers and prime factors. The reason I'm doing this one is because I see a lot of problems where people need to find things like least common multiples, greatest common divisors, they need to simplify roots, and they're not doing this with prime factors, which is the best way to do this, especially when you get into larger numbers. And I think people aren't learning to find the prime factorization, which is a really fundamental skill in math. So I'm going to review prime numbers and prime factorizations of numbers, of composite numbers, and then we will take a look at how we can use this for some of these things like least common multiples. So let's start out with what a prime number is briefly. A prime number is not divisible by any other number except itself and 1. So 1, 2, 3, 5, 7, 9 is divisible by 3, but 11 is prime, 13 is prime, 15 is 3 times 5, so the next will be 17. These are prime numbers. So there are a number of ways to find these, and in fact there's a whole lot of mathematical problems, advanced problems dealing with these. How many are there? How far apart are they as you continue? So there's a difference of 1, difference of 2. Up here we have a difference of 4. When you get up in thousands and millions, how far apart are they? Questions like that are things that advanced mathematics and number theorists like to study and try to answer. The first way to generate these was from a Greek mathematician, Eratosthenes of Cyrene. Cyrene was Greek and then Roman, but today it's where Libya is. And his method was to, let's go back. 1 is debatable. Sometimes it's called a prime number. Increasingly today it's not included in prime numbers, and we're going to leave that off. So let's start with 2, 3. I'm just going to list all the numbers. So there you're up to 23, and you can go as high with this as you want to. And at the end of this video, I'll show you one way that I did this in Excel. It's going to be very easy to implement this with programming. If you like to program, there's a lot of ways to do this. Eratosthenes' method was called a sieve, the Sieve of Eratosthenes. So 2 is prime, and we're going to cross out every multiple of 2 because it won't be prime. 4 is not prime, it divides by 2. 6, 8, 10, 12, 14, 16, 18, 20. None of those are prime, they all divide by 2. The next thing that's not crossed out is 3, that's prime. So we're going to cross out every multiple of 3. 9 is not prime, it divides by 3. 12 is crossed out, 15, 18, 21. So those aren't prime. 5, we're going to cross out multiples of 5. 10's already gone, 15's gone, 20's gone. 7's the next one that's prime. 14 is gone, 21 is gone. 11, multiple of that would be 22, that's gone. So these are prime. 13, 17, 19, 23, and you could keep going. This is called the Sieve of Eratosthenes. And he did this thousands of years ago. And this is a way of generating a list of all the prime numbers. So that's a little background on prime numbers. What do we want to do with the prime numbers? Let's get to the heart of the matter here. What we want to do is, most of the ways we're going to make use of these involve factoring the prime. So let's take a number like 84, and let's say that we want to find the prime factors of this. So there's 2 ways to do this. I'm going to do it the way I learned it, the way I usually do it, a very clear methodology. If I divide this by 2, that's the smallest prime that goes into 84. If I divide by that, I get 42. That divides by 2. I get 21. That doesn't divide by 2. The next prime is 3, and that works. That gives me 7. 7 is prime, and I stop when I get to 1. If you're doing this in computer program, you can look for the 1, and that's when you stop. Some people will use a tree sometimes, so you can start with any 2 factors. I could do 2 and 42, and maybe now I do 3 and, let's see, 3 times 14. So I get 2 2s, a 3, and a 7. So if I miss the 2 back up here, I can find it down here. I could start with 21 times 4. I could start with different combinations and keep going until I have primes at the bottom, as long as you recognize these as primes. So those are 2 ways of breaking any composite number down into its prime factors. So why do we want to do that? And I'm going to demonstrate more of this on the document camera, on paper. But let's just talk about why we want to do this. We need least common multiple. So this is the smallest number that's a multiple of the 2 numbers. So let's say we have 4 and 6. So let's see, it looks like 12 would work, but if I want to find that, 4, prime factors of 4 are 2 2s, 2 times 2. And the prime factors of 6 So to be a multiple of both of these, I need to have 2 2s and a 3. And that gives me my 12. We'll do some examples with less trivial numbers on the document camera. But this is used in fractions. If I have something like 3/4 plus 5/6, I need a common denominator. A very common error is just use 24, multiply 4 by 6. But that's not the least common multiple. And because it's not the least common multiple, when you're done adding the fractions, you're going to have to find the greatest common divisor because it won't be in the lowest form. So that's the least common multiple, and sometimes in a math class the problem is just to find that. Sometimes you need to do it for other reasons, such as adding fractions. So the greatest common divisor is the largest number that divides 2 numbers. So let's use these 2 numbers. The first thing I'm going to do is find the prime factorization. So 150, that divides by 2, I get 75. It's not divided by 2, but 3 goes into that. I get 25. So the 150 is 2 times 3 times 5 times 5. And the 216 divides by 2. That gives me 108. That divides by 2, which is 54, divides by 2 again. That is 27, which is 3, 9, 3. Okay, so those are the prime factors of my 2 numbers. So this time I want to see what they have in common. What's the most that they have in common? Well, they both have 2's, but they only have 1 2 in common. This has 3 2's, but this only has 1. We have 3 in both of these, and again I only have 1 3 here. So that's a 3. And I don't have any 5s over here, so I'm not going to have any 5s. So the largest number that divides both of these is going to be 6. That's the greatest common divisor. If I had added my fractions in the last example without using the least common multiple, when I got to the end, I'd have a fraction where the numerator and the denominator had a common factor, or factors. And I would want to find the greatest common divisor to reduce that to the lowest one. So we'll look at that in a bit too. So the last of the simple things to do are to simplify square roots. Or any roots. We'll look at square roots here. But you could do the same thing for cube roots or higher order roots. Let's say we have 76. So let's say I get a result in a math problem and it says a square root of 76. Well, I can't necessarily leave it that way unless there's no way to reduce it. And it looks like there might be a way to reduce it. The way to find that out and to see if there's anything that can come out of the radical is to look at the prime factors. So we divide this by 2. That would be 35 and 3, that's 38. Divided by 2, that's 19, which is prime. So this is the square root of 2 times 2 times 19. So the way to write this in the lowest form would be 2 times the square root of 19. I have a 2 squared under here, which was not obvious, and as the numbers get larger, it's less likely to be obvious unless you actually go back to the prime factors. Using the prime factors, I found out there was something in here squared, which was a 2 squared, and if it's squared under the square root sign, I can bring it out. So this is another basic use of prime factors. One more use is to find all of the factors of a number. So 76, 4 would be a factor, 2 times 19 is 38, that's a factor. So I can look for all of the factors, prime or not. And if I want to list all of the factors, there is a way to do that, especially using a spreadsheet or program. And there's a way to do that using the prime factors and using these to generate all factors. So I'll show you that near the end when I go to the spreadsheet. I have made use of that in my factoring video, and I'll be using it on a rational function that I'll make a video of one of these days. And then the last thing I'll do at the end is that Sieve of Eratosthenes, which I'll show you on the spreadsheet also. So let's use the document camera and ultimately Excel and take a look at how we can do some examples of these that don't have such trivial numbers. And so when you need to do these things and you need to work with especially larger numbers, it's extremely beneficial to be familiar with these prime factors and how to find the prime factors, and this will let you find common multiples, common divisors. You can simplify roots. You can do a lot of things with these prime factors. So that's it for the whiteboard, and let's go to the document camera and look at a few examples. Okay, so here we are at the computer rather than the whiteboard, and I'm going to do a couple of examples, first with least common multiple, and use that to add a couple fractions. Then I'm going to do a greatest common divisor to simplify a fraction. We'll look at a couple of roots to simplify that, put those in simplest form. We'll find all the factors of a number, and then we'll go to the spreadsheet and do that with the prime factors. And I'll finish with my Excel version of the Sieve of Eratosthenes. So let's start out with an example of the least common multiple. So let's say we want to add two fractions here. let's say we have 7 over 308 plus 3 over 70. Well, I need a common denominator here, so I need a multiple of both 308 and 70. And I want to use the least multiple, the smallest multiple I can. So let's go back and use our prime factors for that. 308, let's find the factors of each of these. There's 308. Okay, so I have my prime factors, and I need to have something that includes all of these. So I'm going to need, let's see, least common multiple is going to have 2 2's, and that covers this. I need a 5 from here, and I need a 7, that's in both of them, and I need an 11, and that turns out to be 1540. So my common denominator is going to be 1540. 308 is, what do I have to multiply that by? Well, the 308 has 2 2's, a 7, and an 11, so I'm going to have to multiply that by 5 to get my common denominator. And the 70 has a 2, 5, and 7, so I have a 2 and an 11 I need, so I'm going to have to multiply that by 22. So I come back here, my 308 has to be multiplied by 5, so that's 7 times 5 on the top. The 3 has to be multiplied by 22 along with the 70. And this is 1540. And this turns out to be 101 over 1540. Sometimes when you're done, you'll still not be in lowest terms. You use the least common multiple. That can happen in certain types of problems, so you should check that this is in lowest form. But 101 is prime, so this is actually in the lowest terms. So that's an example of using the least common multiple to find a common denominator to add 2 fractions. These numbers are a little bit larger than what we did on Whiteboard. So let's say we didn't do that properly and we did what people do, especially with smaller numbers. Let's say we just took a common denominator to be 308 times 70. A lot of times people don't find the prime factors and they just multiply these two, and that is a common denominator. It's not the best one, but it'll work. So now we have 7 times 70, and we have 3 times 308. And if I did it this way, I would end up with 1414 over 21,560. So this is not, in fact we could see that it divides by 2 in the top and bottom. So we know this is not in the lowest terms. We need the greatest common divisor, the biggest number that we can divide both the numerator and the denominator by. We could start factoring out whatever we notice. We could obviously take a 2 out of each of these, and we could look and see whether we can take another 2 out. Just kind of a hit and miss approach, and that's what people often do. But you can miss one that way. There might be a factor of 13 or 19 or something that's not obvious. So the better way to do it is to look for the greatest common divisor. And we need to factor these. We need to factor 1414, and we need to factor this huge number over here. So let's find the prime factors of those two things using my method rather than a tree. So I'll go ahead and do that. Okay, so now I have a bunch of factors for each of these, and in order to find the greatest common divisor, I need to find everything that these have in common. So there's a single 2 in common. There's only one 2 in common. This has 3, but the only one it shares is this one. There's a 7 in common. and there's nothing else in common because this has a 101. And actually, once we know that there are only these three factors, we could just try these three in the larger number. But I want to go through the whole methodology here, so and it looks like I went off the bottom here, but our greatest common divisor is going to be 14. And that means I can divide my numerator by 14 and my denominator by 14. And if I go ahead and do that, the top you can see you'll get 101, and on the bottom you'll get the 1540. So we didn't start out adding our fractions the right way, and we ended up with much larger numbers than we needed to end up with because we didn't bother finding the factors up here. Then we had to find the factors down here in order to reduce it back into lowest terms. So, and even if you do it right in the first one, it's better to check at the end, but you won't have such huge numbers. Okay, here we ended up with these huge numbers that we don't need to work with. So that's an example of the greatest common divisor. Let's look now at just a couple of square root simplifications. So let's say I have 70,000, and I want the square root of this. Well, I can obviously pull some things out of here. It may or may not be obvious what you can pull out of here. 10,000 is 100 squared, so this will be 100 square root of 7. But if that's not obvious, let's, and it won't be obvious to everybody, let's divide this. 2, okay, let's just find these factors. I'll do this again, fast forward. So if we finish that, running out of my page here, but if we did finish that, what we would get is 70,000 is equal to 2 to the 4th. There's my 4 2's. I would also have 5 4 times and a 7. So I have a square root of 2 to the 4th. Well, let's write that as 2 squared times 2 squared times 5 squared times 5 squared times 7. If something's squared underneath the square root sign, I can bring it out in the front. So this is 2 times 2 times 5 times 5. And this is 4 times 25, or 100 square root of 7. So this one is actually not as complicated as others might be. And as I pointed out, you might notice that 10,000 is 100 squared. Some people would notice that at the beginning. And we can do this with the cube root. If we have, let's see, I'm just going to do this over here before I go to a new page. Let's say we have cube root of 2662. So I want the factors of 2662 this time. So the 2662 is 2 times 11 cubed, and I'm taking the cube root this time, so I could rewrite this as the cube 11 times the cube root of 2. And this one isn't so obvious when you start out. You're not going to see that 11 cubed is in here. Very few people, if anyone, would notice that off the bat. We found that by using the prime factors. When you're doing math and you're taking a test or doing a problem, this is really not the final form. If it's a test or a quiz, you'll lose some points here for leaving it this way. You're usually expected to put it into the simplest form. And we can use our prime factors to do that. So let's look at the last thing that we want to do, and that's to use the prime factor to find all the factors, which is going to be best done on a spreadsheet. But let's start out, let's use a reasonable number for this. Let's use 60. We want to find all the factors of 60. And we can list them in this case. This is probably getting to the borderline size of the number I would list them for, but 1 goes into that, 2 goes into that, 3, 4, 5, 6, 7, let's see, 6, the next one would be 10, and then 12, 15, 20, 30, and 60. I should have 12 factors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can start going backwards, and I'll come back to the Sieve of Eratosthenes with this too. The square root of 60 is 7 point something. It's right here. So when I get to 6, I can start going backwards actually. I have 6 times 10. The 5 is going to have another factor with it. That's 5 times 12. And I'm going to end up with the other 6 factors over here. So I'm able to list these in this case. With some numbers and larger numbers, that's going to be hard to do. And one time when we need to do this is factoring polynomials. I have a video on factoring polynomials, and I do this. You'll see this method used in that video with a spreadsheet. So these are the factors, and I'm going to find them from the prime factors. I'm using the spreadsheet in a minute. So let's find the factors of 60. Okay, so we have 2 2s, a 3, and a 5, and I missed a 2, so they aren't in order. They don't have to be, but I usually try to keep going from smallest to largest. So these are the prime factors. So let's see how we can use these prime factors to generate all of the factors. And let's go to the spreadsheet for this. So here we are on Excel. And I started out by putting in my prime factors. 2 2s, a 3, and a 5, and I'm going to generate all the factors. So I'm going to build this kind of like I would with the truth table, if you're familiar with powers of 2. I'm just going to alternate 5, 1, 1, 5, 1. I'm going to alternate each one. And the 3, I'm going to alternate every 2. 2 3s, 2 1s. And now I'm going to have to double this one, because for the next one I'm going to do 4. 1, 2, 3, 4. And I'm going to double this one. So this 2, I'm going to have 8 at a time. Okay, looks like I got an extra row in there. So these are all the combinations of factors. If you've looked at all the combinations and permutations, these are all the basically permutations of the 4 factors. And here I was alternating every 1, 2, 4, 8. So I'm going to have 2 to the 4th, or 16 possible factors. So to find each factor, I'm going to just multiply each separate combination. So this is 2 times this times this, because they just multiplied across the row. So this is my 60. And I'm going to do that for all of the combinations or permutations. So these are all the factors of 60. There's 16 and we only had 12. So what's up with that? Well, that's because we have a multiplicity or duplicate factor here. We have 2 2s, and that gave us some duplicates. So we will find all the factors, but in some cases we will have them listed more than once. Let's take a look at that. You can see why that happens. Let's just sort these. So these are all my factors now sorted from smallest to largest. Here is a 2. See, this is a 2 because I have the first 2. And the next one has only the second 2, and it gives me 2. So down here I'm also going to have one to strike out. This 6 uses the first 2, and the second 6 uses the second 2. That's going to happen on the 10. And it looks like it happens on the 30. So if I cross out those 4, I have my 12 factors. And you'll notice when I factor the polynomials that I also have the negative values. So we've glossed over that so far in this video, but if 10 is a factor, minus 10 is a factor. So these are my positive and negative factors. When you get into really large numbers, and if you have to factor a polynomial that has a really large trailing constant, this method is hands down the best way to do it if you have access to the spreadsheet. Otherwise, you're going to just try each of these factors one at a time, and you're going to have to find all the factors, and it's going to be really long and tedious without using the spreadsheet. When we do use a spreadsheet, though, we're using our friends, the prime numbers. So this is another application of the prime factors of a number. So let's finish with the Sieve of Eratosthenes, and this is my method. It may or may not be a great way. There are lots of ways of doing this. There are probably some that are more efficient, some that are more eloquent. But I listed in the first column all the numbers, and I went up in my example here to 200. So we start by crossing out all of the 2's. So in this column, this is mod. It just means if there's nothing left when you divide by 2, then get rid of it. If there's no remainder. 3 is a remainder when I divide by 2, so keep it. And that's what this mod up here is. That's modular arithmetic. And then I go to the next column, and this time I'm looking at the last prime, the 3. So I'm using the B1 here. And I just get rid of all multiples of 3, just using the same method. And so I keep the 5, I keep the 7, the 9 goes away. So I'm ending up with my primes along the axis here. And actually I can stop after 13. At 13, everything below that is prime. None of those will get eliminated. And let me go. And that's because if you come back here, this the square root of 60 was where we could stop looking for factors. When we got above 6, we were actually at 7 point something or whatever. But when I cross that, I don't need to keep looking. I can just use the ones I have. And that same thing is true for the Sieve of Eratosthenes. The square root of 200 is square root of 2 is 1.41, so this is going to be about 14.1 something. So once I'm above 14, I don't really need to keep looking anymore. So at this point, everything that's still left in the column hasn't changed. I kept going at the beginning just because I hadn't thought much about stopping there. But the other thing is that these numbers are not real organized, and so I can keep going. If I want my result to be a list of numbers, if I want it to be a list of numbers along the top row, I can just keep spreading this across. And I copy this across, and I'm up to 151 on the top there. Let's keep going till we get up to 200, and I'll get an error and I go too far. Okay, so I went too far. Formula's not working anymore over here. And the first row now has all my prime numbers up to 200. Of course, you could go up to whatever number you want. And I didn't really need to do those extra columns to find those numbers, but I did that in order to get them all into the top row. So that's my kind of off-the-cuff Excel version of the Sieve of Eratosthenes for generating a list of primes up to some number. As I said, there's probably more efficient ways. There are some tricks for making it more efficient. If you're really into programming and computation, you can delve into that more. Here it's just an example about primes and where they came from. So that's it for the prime numbers. Okay, so that's it for prime numbers. That was plenty, maybe more than enough for some people. I hope most of it you find applicable and helpful. I hope it elucidates some things about prime numbers. I hope it helps you find least common multiples and greatest common divisors and work with fractions properly. I hope it helps you simplify roots properly. If you're a little more advanced than that, the factor part, finding all the factors, is a nice application and sometimes useful also. And then we had a little bit of historical background about primes and where they come from, and the Sieve of Eratosthenes that goes back to Cyrene and the Greek and Roman period. And a little bit of spreadsheet work on that. So as I have on most of my videos, if not all, I will post on my website the spreadsheet that I used here, and there'll be a copy of that. So if you want to look into that and delve into that, especially the sieve part and the formulas, you can download it from jamesfrankenfield.com. In the academic library, there's a collection of videos that are on YouTube, but there are also supporting materials like the spreadsheets. And there are also some other problems and things in there as well under academic library. There's also a tutoring section. If you need help, please keep me in mind. I offer tutoring. I can help with one session at a time or one short topic, or I can meet regularly. I'm also developing some courses that I'll be teaching online, short and full courses. So that's it, and we'll see you next time. Bye.